Right, so welcome to the last lecture of selected topics in graph theory this semester. And as a sort of a pinnacle of this series of lectures about expanders, we will give today a proof of one of fundamental results in complexity theory in the last 20 years, which is sometimes dubbed L equals SL, but a more explanatory title of this lecture could be rather Undirected Reachability in Logspace. Yeah. So as I said, this is a major application of expanders in a complexity theory problem, and the problem that we will be considering in this lecture is reachability. So this is a very basic problem that you have seen many times throughout your studies. So you are given simply a graph G. Yes, you are given two vertices S and T, and just is there a path from S to T? Can I reach T from S starting walking from S? Yeah. So of course, if I state the problem like this, you can ask whether the graph should be directed or undirected. Yeah, it may be that the graph is undirected, and this essentially boils down to S and T being in the same connected component of the graph, or the graph is directed and it is a little bit more delicate, then the path needs to follow the directions. Yeah, so this is directed reachability and undirected reachability. So like most classical approach, probably during the first lecture on graph algorithm that is observed is to do BFS or DFS. So any graph searching algorithm solves this problem in linear time by essentially searching through the space of all the paths that start from S, and then in both BFS and DFS you are using linear space. For the BFS, this is linear space for the queue of vertices to be visited. For the DFS, the linear space is taken by the stack of consecutive recursive applications of the search. Yeah. So in this talk, we will be concerned about getting better space complexity for reachability. In particular, what we will be wanting to have is to have the space complexity, say, even order log n, but maybe a little bit less ambitious goal would be, say, polylogarithmic. Yeah, so this is already a little bit from the first point of view a little bit fishy, because the graph itself consists of n vertices and m edges, so the description of the graph takes linear space. But as usual in complexity theory, we will be talking about getting a sublinear space complexity in the following model, that essentially we are given a graph, and the graph is there on a read-only tape of a Turing machine solving the problem, and then we can essentially read this graph from a read-only memory. And then apart from this graph that we have a read-only access, we have some small amount of working memory. It will be called a working tape. Yes, where we can store some auxiliary data about the computation. And we would like to minimize the amount of working space that we use. So I'm saying here read-only tape, working tape. We will actually not be using Turing machines. Hopefully, we will be using some kind of an intuitive understanding of a RAM machine with Logspace, logarithmic space complexity, where essentially we will be measuring the amount of working memory that is required by the algorithm. So what can be done if we are given only a limited amount of space, of auxiliary space that we can in which we can solve the problem? So first of all, if you allow non-determinism in your algorithm, so if the algorithm can guess some things, and then using this guessing is only required to show a witness of reachability from S to T, then you can easily see that reachability is in non-deterministic log space. Because if you want to find a path from S to T, and you are allowed to do some non-deterministic guesses, then you simply non-deterministically start with S, and non-deterministically just follow some edges, guessing a path from S to T. And the only thing that you need to remember during this algorithm is where you are actually at this point during the process. So if you are able to, by following edges of the graph, to move like a token from S to T, then definitely you have found a path from S to T. Yeah. So this proves that reachability is in the complexity class NL, which stands for non-deterministic space order of log. Yeah. So I'm now giving some complexity theoretical background of the results. So for those of you who have done complexity theory, this should be pretty transparent what I'm saying now. For those of you who haven't seen the complexity theory, this will not be necessary for the understanding of whatever comes later. But meaning this background is actually quite important to understand the motivation of what we are doing. Okay, anyway, reachability is therefore in non-deterministic log space, and by standard determinization of the theorem of Savage, you can prove that you can solve the directed reachability, so reachability in directed graphs, in space that is quadratic in log n. Yeah, so in space log square n, and then the running time unfortunately blows up to quasi-polynomial. Yeah, so you can actually get a polylogarithmic space. The time complexity goes up, unfortunately, but you can do something. Yeah, but we would like to get something even better, namely to get space to something subquadratic in log n, and ideally we would like to have order of log n space. Yeah. So there are problems with this as long as you are thinking about directed reachability. Namely, directed reachability is a classic NL complete problem in the sense that it is complete under log space reductions for the non-deterministic log space. So this means that if we had a deterministic order of log n space algorithm for directed reachability, then we would have that that L is equal to NL. So every problem that is in non-deterministic log space can be determinized into an algorithm, admits an algorithm with space complexity order of log n that is deterministic. Yeah, so this is an outcome that is pretty unlikely. And therefore, we assume that this is not the case. So for directed reachability, this would be a major breakthrough in complexity theory if this was the case. However, what about if we restrict the attention to undirected reachability? Because intuitively, undirected reachability is much simpler somehow than directed reachability. The structure of connected components in an undirected graph is much easier or simpler to understand than the structure of reachability in a directed graph. So maybe for undirected reachability, we can do something better. And indeed, this is the case. So the theorem that we will prove during this lecture using expanders is the theorem proved by Reingold in 2005 that undirected reachability can be solved by a deterministic algorithm that uses only logarithmic space, so order of log n space, right? So this is a major application of expanders, and Reingold, together with two other people, got a Turing Award for his work on this in particular, but more generally on the work on expanders and on the work on zig-zag products in particular. Good. So this is what we are going to be focusing on today. Are there any questions about our goal?
Do we want polynomial algorithm or quasi-polynomial will also?
You mean in time complexity?
Yes,
right?
in time.
So if an algorithm works in space order of log n, then the time complexity is automatically bounded by 2 to the power of order of log n, which is polynomial.
Okay, thanks.
Because the algorithm has no more than a polynomial number of different configurations of what is happening in the working space. So if it used more than a polynomial time, it would automatically loop. And this is a classic argument from complexity theory. Yeah. Good. Any other questions? Okay. If not, then let's move on to actually doing this. So first of all, let's think what actually means space of space log n. What can I store in logarithmic space? First of all, you need to realize that if you are measuring space in the number of bits, then actually storing one vertex of the graph takes a logarithmic number of bits, because there are n vertices. They are labeled with numbers from, say, 0 to n minus 1, and therefore storing one vertex takes up to log n bits, right? So in logarithmic space, what I can do, I can only store a constant number of identifiers or vertices. Yeah, so this is very restricted. And second, what we will, what you can store in logarithmic space is that you can store actually a stack or a queue or some data structure of size that is logarithmic in n. Yes. However, then the value stored in the stack needs to be of constant size. Yeah, because then even if they were of logarithmic size, you would actually end up with a space log square n. Yeah. So these are two main things that you can store in logarithmic space, and we will use sort of both of them. Okay, so let's first give some ideas on why this should be actually achievable. So first of all, there's a very easy randomized algorithm working in logarithmic space. Yeah, so in a sense, this algorithm will try to find a path, and if there is a path, if there is no path, it will never be able to find a path, and if there is a path, then it will be able to find this path with good probability. Yeah, and the main idea is the following lemma that is not too hard to prove, and we will actually prove some variant of it, some weakening of it during the tutorials. If that randomly walking on a graph is a good algorithm. Namely, if you have a graph and S and T are in the same connected component, then if you start in S, yes, and you just randomly walk in this graph, always pick a uniform at random a neighbor and go to a neighbor, and if you walk for long enough, say if the n is the number of verts of your graph, then you walk for n to the 10 steps. In this way, then if S and T are in the same connected component, with high probability, we eventually during this walk reach T. Yeah. So a long enough random walk eventually reaches all the vertices of the connected component. And this is kind of intuitively should be true. Yeah? And therefore, this is a very easy algorithm that solves the problem in a randomized way, because the algorithm just starts at the vertex S, and for say n to the 10 times randomly picks a neighbor of the current vertex and moves to this vertex, and whenever if at any point the target vertex T is reached, then we return yes, there is a path from S to T. Yeah, and otherwise, if during this n to the 10 steps we have never found a vertex T on our way, then we actually answer no. Yeah, so this algorithm, therefore, if S and T are in the same component, then this algorithm will always answer no. Yes, and if are not in the same component, it will always answer no. And if S and T are indeed in the same component, then it will answer yes with probability at least half, just from this lemma. Yeah, because from this lemma it follows that t will be reached with probability at least half. So this is a one-sided error, randomized. So what is the space complexity of this algorithm? What do we need to store during the execution of this algorithm? Well, we need to store the current vertex u. So this is log n bits to store vertex u. And moreover, we need to store I, the counter. Where are we during the random walk? And this is say 10 log n bits, because we need to store it in binary, and this counter goes from 1 up to n to the 10. Yeah. So all in all, this amounts to order of log n space. Yeah, so this already is a very good indication that the undirected reachability problem is much simpler than directed reachability. Because for directed reachability, because it is null complete, you do not expect that such a randomized algorithm works happens, because then every non-determinist, every problem in an L could be solved by such an algorithm. And this will be already a big collapse in complexity theory. So this already shows that there is some improvement possible due to assuming undirectedness. Okay, so this was one intuition, and now let's see the second intuition. So imagine that your graph has some structure already on it, and this structure is a kind of inspired by whatever we were doing during the last 3 lectures. Namely, assume that the graph is already, let's say, a good expander. In particular, it is deregular for some constant d, yeah, and it has low diameter. It has diameter logarithmic in n. And then the idea is that if the diameter is small, then you can trim the depth first search at the depth being the diameter. Yeah? Because if there is if the distance between S and T is at most log n, then the depth first search will need just log n steps to get there. Yes, and so you can immediately trim the recursion tree of DFS at the depth being the bound on the diameter. Yeah. So the natural way to implement it would be the following pseudocode here. Unfortunately, we will have some pseudocodes during this lecture. However, I believe that this is a bit necessary when you are doing algorithm with bounded space resources, because you need to really understand what is going on in the algorithm. Yeah. So the natural way of implementing such a DFS would be as follows. So the DFS takes two values, the current vertex and I, which is the bound on the recursion depth that you are still allowed to do. So you will start with the DFS applied to the initial vertex S and L, the bound on the diameter, and the DFS works as usual. Yeah, if we are already in the target vertex, we return yes. If otherwise, if the counter is 0, so we cannot make any more steps, then we answer no. Yes, and then for if not, then simply we apply the DFS to every neighbor of the current vertex. Yes, and what I should write here is that we return the disjunction or the OR of outcomes. Yeah, so this is the most natural way of writing a DFS. Yeah, so what is the space complexity of this DFS? So if you write it like this, the space complexity will be actually order of log square n. Why? Because this DFS, because it is a recursive algorithm, well, it applies consecutive recursive calls to this, and every recursive call gets the parameter being the vertex it is currently in. Yeah, so the first DFS call will need to remember the initial vertex S, then the first recursive call will need to remember the vertex it is applied on, and so on and so on. And the whole recursion will result in a stack of depth log n L which is order of log n, and every the internal data for every recursion call. So this whole stack of the frames of the recursion calls. Each recursion call, the internal data will have order of log n space. The total stack has size order of log n, so you get order of log n times order of log n, which is log square n. Yeah, because you have log n frames of recursive calls, each consisting of data taking log n space. Yeah. However, this is a little bit stupid, yes, to remember the whole path on the stack if we know that the graph is deregular for some constant d. Yeah, because the idea is that in order to remember a path from S to the current vertex, so essentially what is now happening in DFS, instead of remembering each consecutive, the identifiers of all the consecutive vertices, I just would need to remember, which of the D edges is the first edge, then which of the D edges is the second edge, and so on and so on and so on. Yeah. So in essence, instead of remembering the whole vertex, we'll just put on the stack the indices of edges. Yeah. So I will remember, let's say the first edge was the fifth edge going from S, then I follow the third edge going from the next vertex, then say the 10th edge, and so on and so on. And these numbers are numbers taken from 1 up to D, and D is a constant. So therefore, for each consecutive step of the search, I will just remember a constant number of bits instead of a logarithmic number of bits. Yeah. So here is a way of implementing this so that it works. Yeah. So now to make it more specific and hide less in the recursive calls, I will think that the algorithm, this recursive procedure, doesn't take any parameters. So the DFS prime is a procedure that doesn't take any parameters, and there are two global variables: the vertex I am in at this point and the depth of the recursion, meaning how much depth is still allowed. Yeah. So the DFS prime now works as follows: if the current vertex is already the target, I return yes. If I is equal to 0, so I do not have any more. I mean, I reach the bottom of the tree, I can return no. Yes, and otherwise I am doing the recursive calls. Yeah, so I'm here decrementing the budget for the depth, and then I'm going through all the neighbors of my current vertex. Yes, and all the neighbors, I mean all the indices of edges of edges going out of the current vertex. Yeah, so for every gamma from 1 up to D, I'm now looking at V, the gamma of neighbor of U. So here is U, and here's the first, the second, the third, and the diff neighbor. Yeah, so I imagine that on the adjacency list of the graph, the neighbors are somehow ordered. Yeah. And now if I decide that, say, I'm going from U to, say, the third neighbor V, what I will need to remember is that, okay, if I go from U to V, I need to take the third edge, but if I'm going back from V to U, yes, I need to somehow remember the return address. Yes, so V is also having its adjacency list. Yes, and U is among one of the neighbors of V, and therefore there is some index, say index 5. Yes, such that U is the fifth vertex on the list of V. Yeah, so every edge it has like one index from U to V, and the second index, the return index from V to U. Yeah? So let delta be this return index, so the index of U on the list of V. So now I remember this index delta because it will be useful for going back from V to U, and I can apply my DFS prime in the following way. I move to the vertex V, so I substitute U for V. I apply my DFS prime now with decremented counter and with new vertex. Yeah, so I'm doing something on this vertex V. Yes. And now when I'm finished, I can go back from V to U by just following this remembered index delta. Yep. So now I substitute for U the delta neighbor of U. Here, observe that U is actually equal to V here. Good. So what this algorithm needs to remember, meaning what is the space complexity? Well, it is still a recursive algorithm, so it applies the consecutive applications of DFS prime. And the only thing that this algorithm needs to remember between this line and this line, yes, is this delta, which is a number from 1 up to D. Yeah. So the stack of the recursion will consist of the consecutive deltas remembered for the first, for the second, for the third, and so on, recursive call. So we will in total have a stack of order of log n values, each taking order of log d space. Yeah. And log d, because we assume that d is a constant, is constant, right? So this is a stack of size log n of constant of values with constant bit size. Good. So this is an implementation of this idea, assuming that the graph is deregular for a constant d that takes order of log n space. Observe that in both of these DFSs, here and here, yes, we did not use any like a global table for saying who is visited and who is not. In particular, I can go to a vertex and then go back. I do not remember the previous guy, but this is okay. If there is a path from S to T, it will be discovered by this algorithm. It just tries all the possible paths of length at most log n. Good. So this is a basic algorithm, assuming that the diameter of the graph is small. It's this logarithmic. Are there any questions to this algorithm? Or if you are happy with it, maybe you can put a +1 in the chat. Okay, I see a number of +1s, so I hope that for most of you this is fine. Good. So now we are going to use the second intuition to get a deterministic algorithm. And the key idea is that if we start with a graph that is any graph, we will sort of turn the graph into an expander. And then once it is turned into an expander, while preserving connectivity, we'll be able to apply this algorithm that we just seen before. And we already sort of understand the toolbox for turning a graph into an expander, because during the last lecture, we actually constructed an expander using these tools. Namely, the tools were squaring and zigzagging. Yeah. So one of the operations was an operation of squaring a graph, so making new edges out of all the walks of length 2. And this operation of squaring, it improves the spectral gap. Yeah, so the spectrum gets more concentrated, yes, while the degree is getting larger. Yes, while the zigzagging operation was an operation that was somehow complementary to it, namely the spectral gap goes a little bit down. Yeah, but the degree is getting very, very much down up to a constant value. Yeah, so we know that we can sort of alternate between these two operations, squaring and zigzagging, in order to keep both the degree and the spectral gap in check. This was the idea behind the previous lecture. And what we will be doing now is that we will be using this alternation between squaring and zigzagging to iteratively turn a graph into a good expander while keeping the degree constant. Good. So that's the main idea. So now we proceed to the implementation. So let's make some assumptions first. First of all, I will assume that the graph is actually connected. Yeah, in a sense, I imagine that I've got a connected graph and to vertices S and T, and I would like to prove to you that S and T are in the same connected component by showing a walk from S to T. And so essentially what is done in the general case is that the whole construction that we will be doing, it will be this squaring and zigzagging, so it will preserve all the connected components. Namely, every connected component will stay connected during all of the operations that we'll be doing. So therefore, what will be actually happening is that every connected component will turn into an expander. And then we will apply this algorithm, this bounded depth DFS from S. And if T was in the same connected component, it will be discovered. And if T was not in the same connected component, then clearly it will not be able to be discovered. Yeah, but for the purpose of the whole spectral analysis, I will assume that G is connected. Yeah. So in other words, I restrict my attention to the connected component of S. Yeah. And second, I will assume that the graph is free regular. So it is already has bounded degree, and in particular, it has all the degrees bounded by 3. And this can be very easily done by replacing every vertex with a cycle. Yeah. So whenever I have a vertex, say, of degree 5, I replace it with a cycle of length 5, like that, with the original edges being rewired to the different vertices on this cycle. Yeah. So for instance, if here was a vertex of degree 3, this vertex is being now replaced with a triangle looking like that. Yeah. So every vertex is now being dissolved into a cloud. And if I now want to check whether, say, S is connected to some vertex T here, I need to pick any vertex from here and any vertex from the cloud of T, and check whether they are connected in this modified graph. Right. So this preserves connectivity, and it makes the graph free regular. However, meaning we are doing a Logspace algorithm. Yeah, I cannot just take the input graph and rewrite it completely, because this would take like a linear auxiliary space if I wanted to emulate this. So there's a standard trick of doing this. You can use the standard way of understanding it in complexity theory, namely that the composition of two operations that can be done in Logspace can be modeled in Logspace, but there is a more direct way of understanding this. Namely, we can essentially emulate working on this graph G prime by working on this graph G. Namely, the vertices of the graph G prime, what are they? They are actually pairs. Yes, pairs consisting of a vertex of G. Yeah, so the cloud in which my vertex UI is. Yes, and then the index of the edge outgoing of the vertex U. Yeah, so I model the vertex of G prime as pairs. And now if I have some vertex U comma I of G prime, I need to be able to do some basic operation, graph operation in the graph G prime, namely listing the neighbors of the vertex U I. Yeah, so what are the neighbors of the vertex UI? Well, these are U comma I plus 1 and U comma I minus 1, of course, modulo the degree of U, but the degree of U I can also read from the description of G. Yeah, and also there is a vertex V comma J, yes, where V is the neighbor of U that is the if neighbor of U. Yeah, and the J is such that U is the Jth neighbor of V. Yeah. So then from the description of if I want to list the neighbors of U comma I can do it by an algorithm that uses only logarithmic auxiliary space working on the description of G. Good. Any questions about this? Because this is a very basic idea of emulation that will be used very much later on. Okay. If not, then
determine J.
Sorry.
How do we determine J?
How do we get J?
Yeah.
Well, how do we get V first? Yeah, I'm going through the description of G. I'm searching for where is the adjacency list of U. I'm looking at the if entry of this adjacency list. This is V. Yeah. How how do I get J? I search through this description of G. Yes. I find the adjacency list of V. I'm going through it until I find U on this adjacency. And the index at which I have found U is J. Is this clear? Okay. Good. Observe that this algorithm takes linear time, but we don't care. We only care that it takes logarithmic space. Good. Okay, so now we are going to starting with G that is free regular, make the expanderization of this graph. So first of all, let's think about what is the spectral gap of this graph so far. So during the tutorials, we have seen a fact. We actually did not prove it, but we proved half of this fact. That if I have a connected graph that is not bipartite, then actually this alpha, recall that alpha is how much the spectrum is concentrated. Yeah, so this is the maximum absolute value of a non-trivial eigenvalue divided by d, the regularity of this graph. Yeah, so this alpha, which tells you how much the spectrum is concentrated below this d minus, sorry, plus d minus d in this minus d plus d interval. That if G is connected and non-bipartite, then there is actually some gap here. Namely, you do not have eigenvalues minus d or plus d other than this one trivial. Yeah. So all the other eigenvalues are strictly in this interval between minus d and d. Yeah. And if you look at this argument a little bit closer, and this is what we will do during the tutorials, you can squeeze a little bit more. Namely, if you have a deregular graph that is connected, and say for simplicity has a loop at each on each vertex, then I claim that alpha, so this ratio between non-trivial eigenvalues and the trivial eigenvalue, is strictly is smaller than 1 minus some small amount. Yeah, 1 over d to the 4 times n squared. So it is a little bit bounded from 1. Yeah, so on a picture, I've got this interval from minus d to d, and the actual spectrum is a little bit here. Yes, a little bit bounded away from minus d plus d, and bounded away by multiplicative factor 1 minus this tiny epsilon here. Yeah, this tiny epsilon depending on d and n. So now the idea is that we will be modifying the graph G, yeah, in such a way that we will be using the squaring and zigzagging roughly log n times, yeah, to get alpha to be significantly smaller than significantly away from 1. So it will be smaller than 1/2. So in a sense, we'll be using squaring and zigzagging in order to amplify the spectral gap while keeping the degree bounded. And the construction will be very, very similar to what we were doing during the last lecture. Yeah. So first of all, we will need some base graph. This will be an expander. So for the base graph, I take some graph H that is a d to the 16 d comma half expander for some constant d. So during the last lecture, we were using as a base graph a graph that has d to the 8 vertices and is deregular and had spectral gap at most 2 over 5. However, you can use the same construction that we'll finish during this tutorial to get d to the 16 vertices instead of d to the 8. Yeah, so we hard code in the algorithm some base expander H for some constant d that has this property. Yeah, so for which the alpha of H is bounded by 1/2. So this is the base graph that we will be using. Yeah. So now from the graph G that recall was free regular, we make a graph G0. This is the base thing in our construction. I take the graph G and I add many loops at every vertex. More specifically, I add d square minus 3 loops at every vertex. In this way, turning G into a graph G0 that is d square regular. Because all the graphs that the consecutive graphs that I will produce during my construction, they will be all d square regular. Yeah? So what I know about G0, well, G0 is now a connected graph because I assume that G is connected, so G0 is also connected. It is a connected graph that is d square regular, yeah. And definitely it has a loop at every vertex, yeah, because we added a lot of loops at every vertex. So by just applying the lemma that we have seen before, yes, we know that G0 already has a little bit, the spectral gap is already a little bit good. Yes, and now we will take the spectral gap that is here a little bit bounded away from 1 and amplify so that it's much away from 1. So the construction is very similar to what we were doing the last time, namely, in order starting from G0, we iteratively take the 8th power of the current graph and zigzag it with the base graph. Yeah. So in particular, if GT is d square regular, this means that GT to the power 8. Yeah, so to the power 8 means 3 times u square. So GT to the power 8 is what? Is d to the 16 regular. Yes, which means that the zigzag is allowed, is well defined, because the regularity of the graph of the left hand side of the zigzag is equal to the number of vertices of the graph that we substitute with, that we zigzag with, yeah, d to the 16, and therefore this GT plus 1, which is defined as GT to the power 8 zigzag zigzag h, yes, is well defined and is d square regular. Yeah. So this is a valid construction. In this way, I have defined some sequence of graphs. So far, I do not care about the computability of all of this. This is just a mathematical construction. The computation issues we will discuss later. Good. So we have defined this graph G1, G2, G3, and so on and so on and so on. So what we have? So now we need to understand how the spectral gap improves in this construction. So the lemma that we were using the last time and that we actually proved during the last lecture was the following lemma, that if we have already a good expander, G, yes, with some the spectral parameter alpha being alpha of G, then making a zigzag with a graph H can only worsen the parameter alpha by adding alpha of H and alpha of H squared. This was called beta during the last lecture. However, observe that actually this kind of a lemma is a bit useless for us now. Why? Because we start with a G0 whose alpha is almost 1, right? It is 1 minus some tiny epsilon. So if we zigzag with H that has even, I don't know, alpha equal to 1 over 5, this inequality will give you nothing. Yeah, because this plus 1 over 5 plus 1 over 25 will easily go beyond 1. Yeah, so we need to have an understanding of how the zigzag works. Also for graphs G, yeah, where alpha is very close to 1. And this understanding is given by the following lemma, that if I want doing a zigzag with H, then the alpha of the resulting graph is bounded as follows. This is 1 minus, and now I look at how much alpha of G is bounded away from 1, and it is scaled. This boundedness, this bound is scaled by some factor depending on how good H is an expander is. Yep. So on the spectral properties of H. Yeah, so in a sense, this bound says that if for G, here, let's say that here is this -1 and 1, and for G, I've got alpha of G here, yeah, then alpha of G zigzag H will be somewhere here, where how much I go to 1 depends on how good expander, how good are the spectral properties of H. Yeah. So this is a lemma that controls the zigzag product in the neighborhood of 1, let's say. We will not prove it. Meaning, I hope that you can believe me that this bound can also be proved using the same kind of toolbox that we use for proving this lemma. So this is the only element of the proof of the result that we will leave unproven here. Yeah, but we will use this lemma. Good. Any questions? Okay. If there are no more questions, then we can actually use this lemma to analyze our sequence of graphs GT that are defined using this procedure. Yeah. So for the ease of notation, let GT hat be this graph GT taken to the power 8. So then this means that GT plus 1 is defined as GT hat zigzag H. Good. So first of all, we observe that we need to understand how this spectral parameter alpha is being improved during the process. And first of all, we observe that if alpha is larger or equal than 1/2, alpha of GT hat is larger or equal than 1/2, then in the next iteration, when I look at GT plus 1 hat, then actually it will improve. Yes, it will improve by squaring the previous bound. Yeah. So in a sense, if say alpha at the beginning of alpha of G0 is say 99/100, then this will be that alpha of G1 is bounded by 99/100 square, and so on and so on. Yeah. So each iteration, as long as we are above 1/2, each iteration will result in squaring of the previous bound, which significantly gets us closer to 1/2. Yeah. Okay, so let's prove it, and this is just a calculation using the lemma that we already have. Yeah. Right. So let's let x be let's denote by x this 1 minus alpha of GT hat. Yeah. So this is how much alpha of GT hat is close to 1. Yes, and this is so far at most 1/2. Yeah. So what is alpha of GT plus 1 hat? Well, GT plus 1 hat, yes, this is GT plus 1 to the power 8. So then this means that alpha of GT plus 1 hat is alpha of GT plus 1 to the power 8. Yes, this is how alpha is being treated when you take a graph to a power. Right, so we have this inequality here. Yes, this equality here. So now what we are doing, we are recalling that GT plus 1 is equal to GT hat zigzag H. So we are using this lemma that we wrote here in order to say what is the bound on this alpha. Yeah, so because this is a zigzag, I can write this at most 1 minus. Now x is 1 minus alpha of GT hat. Yes, and here I've got this this factor depending on expander H. Yeah, and what we assumed about H, we know that alpha of H, yes, is at most 1/2. Yeah, so H was a good expander, which means that 1 minus alpha of H square over 2 is at least 1 minus 1 over 4 over 2, which is 3/8. Yeah. So now I know that this is upper bounded by 1 minus 3/8 times x. Yeah, because just this thingy is lower bounded by 3/8. Good. So I've got that this is at most 1 minus 3/8 x to the power 8. And now I need to use a magic inequality that I hope that you can also believe me that it is true. That if I take 1 minus 3/8 x and take it to the power 4, then this is upper bounded by 1 minus x for x at most half. Yeah, this is just an polynomial inequality in one variable. Yeah. So now if I apply this, I see that this is at most 1 minus x squared. I apply it only to this 1 minus 3/8 x to the power 4, yeah, which is nothing else than by our initial notation alpha of gt hat square. Good. So here the idea is that because of this zigzag product, the spectral parameter gets a little bit worse. It is multiplied by this 3/8, which comes from this factor from h. But we are anyway taking the whole graph and taking its 8th power. So we are here improving the spectral gap. Yeah. So this worsening of the gap by this factor 3/8 is being amortized by taking it to the power 4, and then we still make another square of the graph, so we actually improve the gap. Good. Are you comfortable with this proof? Maybe some +1s or any questions here? Yeah. If you do not have problems, please put a +1. Okay, I see quite a number of +1s, so let's continue. Okay, so this was the situation where alpha was still above 1/2. Yeah. So at some point the alpha gets to below 1/2, say like that. Yeah. And then I need to make sure that if it is below 1/2, then it stays below 1/2. And this is essentially the same estimation as here. Namely, these steps I can just rewrite the same way. The only moment where we actually use the fact that that x is at most 1/2, yes, was in this estimation. Yeah, to see that that it is being squared. However, now if we have x at least 1/2, yes, then what we have is this 1 minus 3/8 x to the power 8. Yeah, so if now x is at least 1/2, then this is upper bounded by 1 minus 3/16 to the power 8. And you can believe me, I actually checked it yesterday on calculator, and 1 minus 3/16 to the power 8 is actually significantly smaller than 1/2. Yeah, so the same argument here, but with x at least 1/2 gives you a conclusion that if you are already below 1/2, then you stay below 1/2. Good. So this means, all in all, that during this process, I start with a gap that is with alpha, which is very close to 1, but I iteratively get it smaller and smaller and smaller by squaring up to the moment when it drops below 1/2, and from now on it will always be below 1/2. Good. So you can phrase this corollary in a concise way, that if I look at alpha of gt hat at any moment in the process, then it is upper bounded by the maximum of 1/2, yes, and the initial gap to the power 2 to the t. Yeah, because t times you square the initial bound. And recall that alpha of g0 hat, well, we know that alpha of g0 is upper bounded by 1 minus 1/d to the power 8 and square. This is what we observed at the beginning because of connectedness of g0, and now you also know that alpha of g0 hat is upper bound by alpha of G0? Well, because it's just G0 taken to the power 8. So actually it is equal to alpha of G0 to the power 8. So it can only get better. Good. So all in all, we know that alpha of GT hat is upper bound by this. So this means that if I apply this many iterations, logarithm of d to the 8 n square iterations, then what I have here is that this is maximum of 1/2 and 1 minus 1 over d power 8 n square to the power 2 to the logarithm of this, so just d to the 8 n square, yes. And this is around let's see, upper bounded, yes, upper bounded by e, by the inverse of e, which is strictly more than 1/2. Yeah. So this is at most 1/2. So this means that if we apply this many iterations, say capital L, which is the logarithm of d power 8 n square, yes, then we already get a graph whose spectral parameter alpha is smaller or equal than 1/2. Yeah. So applying a logarithmic number of operations in this procedure brings us a graph that is already a good expander. Good. So, and this is the main idea of the whole proof. So what we now know about this graph GL after applying L operation? First of all, clearly it is d-square regular, yeah, because all the graphs G1, G2, G3, and so on during our procedure were d-square regular. How many vertices does it have? Well, it has some more vertices than the initial graph, because every time we're doing the next step of the procedure, we're zigzagging with some graph, and zigzagging, recall, multiplies the number of vertices by the number of vertices of the graph we zigzag with. Yeah? So the size of the vertex set of GL, call it n bar, yes, is the number of original vertices of G0, yeah, which is upper bound by n square, because this is at most this many edges the original graph G has. It is bounded by n squared times the total product of the vertex set of those graphs H with which we zigzagged with. Yeah. So we zigzagged L times, capital L times, and every time we zigzagged with a graph whose number of vertices was d to the 16. Yeah. So here we've got this bound on the number of vertices. Actually, this will be even equality. So how can we bound this? Well, L is logarithmic in n, so it is bound by, say, 2 log n plus order of 1. Yeah. So this is bound by n squared times some constant to the power order of log n. So this is still polynomial in n. Yeah. So all in all, we have polynomial in L in n times a polynomial in n, resulting in a polynomial in n bound. Yeah. So even though we zigzagged log n times, each time enlarging the graph by some constant factor, all in all, we at the end we got a graph that is whose size is still polynomial in the size of the original graph. Good. And this was important because now this means that if I'm thinking about an identifier of a graph, of a vertex of this final graph GL, this identifier takes up order of log n bits. Yeah, because the size of the final graph is polynomial in n. Okay, so what we know about GL hat? Well, we know that GL hat, alpha of GL hat, yes, is at most 1/2. This is the outcome of this procedure that we have, which means that the diameter of GL hat is bounded by the logarithm of the number of vertices of GL hat. Yeah, this is one of the problems we have seen during the tutorials. This was the analysis of the random walk on an expander. Yeah. So this means that the diameter of GL hat is bounded by the logarithm of the number of vertices. So what about the graph GL? Well, GL hat is nothing else than GL to the power 8. So if I can reach every vertex in GL hat in some number of steps, In GL, I need at most 8 times more number of steps, yeah, because paths in GL hat, edges in GL hat are walks of length 8 in GL. Yeah. So the diameter of GL is bound by 8 times the number of vertices of GL, and because n, the logarithm of the number of vertices of GL is order of log n, this means that the diameter of the final graph is logarithmic in the number of vertices of the input graph, and this is important, yeah, because we now know that in order to understand reachability in GL, we need to apply DFS only up to bounded depth, up to logarithmic depth. Yeah. So now the idea is that it suffices now to apply this DFS prime algorithm that we have seen some pages before on the final graph up to logarithmic depth. Okay, so this is the conceptual part of the whole proof. And now what happens is that we actually need to go into some computational details, because this GL graph cannot be constructed explicitly. Yeah, we cannot really apply this construction and construct the graph G0, then G1, then G3, and so on, and all of them store in the memory. Yeah, we need to somehow emulate the consecutive steps of this procedure and be very careful that we do not exceed the logarithmic bound on the space complexity. Yeah. So the conceptual part of the expanderization is now done. Yes. Now we need to understand how to actually implement all of this. Good. Any questions? Okay. If not, then let's go to the implementation details. So let me recall how the procedure DFS prime should be applied on the graph GL. Yeah. So again, if I start with some vertex S, yes, actually this will not be the original vertex S, because the vertex S, the original one, lives in the original graph G. I will need to test reachability between anybody from the cloud of the original vertex of S and the cloud of the original vertex of T, yeah, where the cloud is all the vertices that the original vertex S eventually got substituted with. And I've got this parameter I, which is the length of the recursion, that is the depth of the recursion that is still allowed, and I set it in a priori to 8 times the number of vertices of GL, which is order of log n. Yeah. So these are the initial global variables, U and I. Yeah. So yeah, if we are already in the target, or in the cloud of the target rather, then we return yes. Yes, we kill the whole procedure and we say yes, we have found the path. And we return no, we have not found a path in this branch if the parameter I, the depth of the recursion allowed, already dropped to 0. Yeah. So now after checking this corner cases, we need to actually do the procedure, yeah, the DFS step. Yeah. So we decrement the counter for the depth, and then go through all the neighbors of the current vertex U. Yeah, there are d square of them. Yeah, because the graph is d square regular. Yeah, so we iterate over all the gammas that are from 1 up to d square, the indices of the neighbors of U. So now we look at the vertex V, which is the gamma neighbor of U in GL. Yeah. We get the return index, yes, of U on the list of, so the index of U on the list of V in GL. Yeah. So I'm now just saying what should be done. I did not actually implement it, and it will be non-trivial. Yeah. So then what we do, we move to this vertex V. Yeah. So we substitute U for V. Yeah. And we apply the DFS again with U updated and with with I updated and with U updated. And then when we are done with the DFS prime, we go back to the original vertex U by following this return address that was remembered on the stack here. Yeah? So here again we have a stack of depth order of log n, stack depth order of log n, and each consecutive value that is stored on the stack is one of those deltas. And because deltas are indices from 1 up to d square, I need a constant number of bits to remember each of them. Good. And then we return back to U and we follow with this for loop. Yeah? And once we are done, we restore the original value of I. Yeah. So this is on everything on paper, because we actually did not understand now, if we do not have the graph GL explicitly, how to do all of these operations here. Yes, how to emulate browsing through the neighborhood list in GL. Yeah. So what will be the main procedure that sort of we need to be able to emulate in the graph GL is the procedure that I will call go L from some index gamma. Yeah. So this is a procedure that essentially corresponds to those 3 lines of the code. Yeah. Of finding the gamma of neighbor, finding the return index, and actually moving to this neighbor. Yeah. So to make it more precise, I am having this global variable U, yes, which is a vertex I'm currently in, and this go L of gamma should go from U to the gamma of neighbor of U, which is V. So it should replace actually the variable U, say given by reference, with variable V, with the vertex V. Yeah? So more precisely, I find the gamma of neighbor of U in GL. I remember the return index delta. Yes, I actually do the replacement. Yeah, I move from U to V, and I return the return index for memorization because I will need it later to go back. So this index delta is the return index. Good. So this is a macro, let's say, that is needed to implement this. So I could take all these 3 lines and replace it with go L gamma. Yeah, because then this is exactly what needs to be done here. But the nice thing is that also I can implement this part using also the macro go, using macro go L delta. Yeah. So once I am in V, in order to restore U, to go back to U, I only need to follow this return index delta. Yeah. Then this go L delta will actually return gamma, but it's not needed now. Good. So what we need to do in order to implement this DFS in Logspace, we need to implement this macro, go L of gamma. Any questions? Or maybe +1s, because this is kind of important to understand these precise details. Okay, I see some +1s. Maybe I can clarify something. Okay, if not, then let's continue. This is almost the finish. Namely, we need to emulate the how to implement traversals of neighborhood lists, essentially in the graph GL. And we will also do this by recursion. Namely, in order to emulate the neighborhood lists in GL, we will use emulation of the neighborhood lists in GL-1, which will use GL-2, and so on and so on and so on up to G0. Yeah. So the macro go will also be implemented using recursion. Yeah. So more precisely, I will now write an algorithm for the procedure go t of gamma. Yes, where this works on the graph GT. Yeah. So how this should work? First of all, if already we are down there at the graph G0, then we have G0 essentially there, meaning not precisely because we are still emulating G0 using the very original graph G. But if t is already equal to 0, we already have seen how to emulate, how to implement the neighborhood lists in G0. So if t is equal to 0, we just do the job in G0. So this we have already seen. So this is the bottom of the recursion. So now what happens if I'm working with some graph GT for t at least 1? So recall what was GT. GT was defined as GT minus 1 to the power 8 zigzag h. Yeah. So now we need to understand like how to implement neighborhood lists in GT based on the understanding of the neighborhood lists in GT minus 1. Yeah. Okay. So first of all, what are the how we can interpret the vertices in GT? So a vertex in GT, say U, yes, can be interpreted as a pair a comma x. I already wrote it here. It can be interpreted as a pair a comma x, where a is a vertex of GT minus 1 and x, yes, is a vertex of h. Yeah, because recall that how the zigzag worked. We took every vertex of GT minus 1 to the power 8, which is a vertex of GT minus 1, and we blew it up to a cloud consisting of as many vertices as the graph H has. Yeah. So here are those clouds, and every cloud is a blown up copy of H. Yeah. And how the edges are working in the graph GT? Well, if I want to check whether there's how an edge arises in the graph GT, it arises by making one step in a copy of H, then making one step in the graph GT minus 1 to the power 8, and then making one step in the graph in another cloud of H. So now observe that a single step in the graph GT minus 1 to the power H actually can be represented by 8 consecutive hops in the graph GT minus 1. Yeah, so every edge in the graph GT corresponds to one step of a walk in H, 8 steps of a walk in GT minus 1, and then one step of a walk in H again. Yeah? And in particular, this index gamma that is given to us, which neighbor are we now looking for? Yes, is actually can be interpreted as a pair of indices, one index alpha here and one index beta here. Yeah, because the index alpha tells us what step we should do in the first cloud of H, then at which vertex we arrive at uniquely defines to us what steps we should do in this graph GT minus 1 to the power H, and then the index beta tells us how to proceed in the last cloud of H. Yeah. So I can interpret this gamma, which is from the set 1 up to d square, as a pair of indices, alpha and beta. Okay, so how do we now make this emulation? Yeah. So how do we actually get the neighbor of a comma x in the graph GT? Yeah. So first of all, we need to make this step in the first cloud of H. Yeah. So this consists of replacing x with some x prime, which is the alpha neighbor of x in H. Yeah. And maybe I will redraw it. Yeah. So here is this first copy of H that corresponds to the cloud of vertex U. And here we start with X, and we are moving along index alpha, yes, to some X prime, and there is some return index alpha prime. Here, maybe with a different color. Yeah. So this is a computation that is being done purely in the graph H, which is of constant size. So this part can be even hard coded in some table in the algorithm. Yeah, but still, I've got some index alpha prime, which is the return index, and it is a number from 1 up to D. Yes, it is the index of X on the neighborhood list of X prime. Good. So now when I have done this, I ended up with a vertex U comma X. This is a vertex U comma X of the graph GT. Yes. So now we need to make those 8 steps in the graph GT minus 1. And which steps should we do? Well, the index X should tell us, yeah, because the vertex of H I am in uniquely tells me where should I go in the graph GT minus 1 to the power 8, yes, and where should I go in the graph GT minus 1 power 8 is like an 8 tuple of steps in the graph GT minus 1. So the index X, which is a vertex of the graph H, which is an index from 1 up to D power 16, yes, I can reinterpret as an 8 tuple of pointers of which steps to do in the graph GT minus 1. Yeah. So this vertex where I end up here in this cloud tells me exactly which steps I should do in GT minus 1, those 8 consecutive steps, because it tells me exactly what step I should do in this whole graph, this 8th power. Yeah. So I can interpret now X, which is a vertex of H, as an 8th tuple of indices from 1 up to D squared. And what I need to do, I need to actually now do those 8 steps. So in the graph GT minus 1, yeah, I perform 8 times the procedure go. Yeah. In this way, from maybe to redraw the picture, yes, we have made 1 step in here. Yes, now we are moving with 8 steps in the graph GT minus 1, yes, using consecutive indices Xc1, Xc2 up to Xc8 for those go operations, and each of those go operations in the graph GT minus 1 gives us some return index, in the sense like how I should go back here. Xc1 prime, Xc2 prime, and so on, Xc8 prime. So by doing this, I apply this to this vertex A of GT minus 1, and I ended up with some cloud B. Yes, so A is being transformed by those operations go into B, which is another vertex of GT minus 1. So this is just application of where I should go in GT minus 1 based on where I ended up in the cloud, in this cloud. Good. So now I applied all of this, and one could think, okay, I ended up in this cloud of B, but in which particular vertex of this cloud of B I ended up with? Well, actually, in the vertex that is the vertex C8 prime, C7 prime, and so on, C1 prime, because this should be the vertex where when I apply those return indices, I exactly go with this path back. Yeah. So this is my vertex Y. Yeah. So now I am currently at the vertex B comma Y. Yeah. So now the last step of the zigzag product is performing a step in this copy of H corresponding to the vertex B. Yeah. So now I am using my last index B from this pair gamma to go from this. I called it Y prime probably. Yeah. To go from this vertex Y prime to the final vertex Y. Yeah. And this is my final vertex, which is the gamma neighbor of the original vertex A comma X. Yeah. So in order to actually implement the move, yes, the variable A got already replaced by B using this go operation. Yes. And now, in order to also modify this last step where I am in the graph H, I should replace the data where X is stored with the index of Y. Yeah. So in this way, I have changed the vertex A comma X to the vertex B comma Y throughout all this process, and the return index is how should I proceed if I wanted to go from B comma Y to A comma X by reversing all of this. Well, I should use the return index B prime here, yes, which was computed here in this cloud. Then I would need to then where I am in this cloud tells me exactly how I should proceed with this path back. And then once I am back in the cloud of A, the index alpha prime tells me how I should get to A comma X. So the delta that I return is B prime comma Y, alpha prime, beta prime comma alpha prime. Good. So all in all, how much space did we use in this algorithm? So the depth of the recursion of all of this is L, yes, because we start with GL and then we recurse on consecutive go operations every time making this T1 smaller. Yeah, and so the depth is log n. And what internal data this algorithm go needs to remember, yes, when it is making a recursive call here? Well, it needs to remember this index alpha prime because it will be needed at the end. Here, it was pre-computed, so this needs to be remembered in the on the stack. It needs to remember also the previous x's. Yeah, so whenever I'm computing, say, I'm applying the third go, I need to remember the xc1 prime and xc2 prime that were computed before. So the x's needs to be remembered. And well, I can also remember where I am in this process. Yeah, so essentially, these are the three things that needs to be remembered here. So this is an index from 1 up to 8. Nothing to worry about. These are indices from 1 up to d square. So also I need a constant number of bits to remember each of them. And alpha prime, this index at the beginning, yes, this was an index in H, which is also from 1 up to d. So again, a constant number of bits is needed for storing. Yeah. So the internal information for every recursive call of the procedure go takes order of 1 bits. I've got total recursion depth logarithmic in n, so I've got order of log n space in total. Good. Okay, this was a little bit technical. I hope that I did not lose all of you during this procedure, but essentially what this boils down is that this zigzag product has this very nice property that it is a very concrete operation. And if you apply this operation sort of iteratively, making larger and larger graphs, you can emulate the neighborhood lists of the next step in the construction using the neighborhood list in the previous construction. This is a little bit technical, but I hope that I convinced most of you that this can be done, so that at every point in this recursion, I only remember a constant amount of information. Yeah. Other questions? This, and yeah, so just to finish, so we have given an implementation of the procedure go in logarithmic space, which was enough to do the DFS prime in log space, yes, which gives us the undirected reachability in log space. And this finishes the proof of the result of Reingold. Are there questions? Okay, if not, then thanks a lot for this lecture, and thanks a lot for the whole semester. I hope you enjoyed this course, both the lectures and the tutorials, and hopefully also the exam. Remember that in USOS there are student feedback forms that you can and you ought to fill in. I will also recall this during the tutorials, but we will be very happy to hear the feedback from you about those lectures and this course in general, because it's already I think 4th time this course is given, so I hope that with every iteration it can get a little bit better, and your feedback is essential for that. So thanks a lot, and I hope to meet with you in half an hour for the last tutorial.